Hilbert's hotel is already full, yet an infinite line of antique buses has just arrived, each carrying an endless number of new passengers. To fit everyone in, we can try an algebraic solution using prime numbers. Each passenger is assigned a room by calculating 2 to the power of their seat times 3 to the power of their bus. In this model, we treat original guests as bus 0, which maps them to simple powers of 2. New arrivals use both the seat and bus values as exponents to find their specific room number. Because every integer has a unique prime factorization, no two combinations of seat and bus will ever produce the same result. The room assignments will never overlap. This collision-free state is what mathematicians call an injective mapping. While the algebra works, this method creates a massive, invisible problem. By relying solely on primes 2 and 3, we are leaving the vast majority of the hotel empty. If we check the registry for room 15, we find it has no occupant. The number 15 is the product of 3 and 5. Because our formula only uses powers of 2 and 3, a room that requires a prime factor of 5 is mathematically unreachable. This gap isn't an isolated case. Every room number that includes any other prime, like 5, 7, or 11, remains a void. We've avoided collisions, but we've wasted millions of rooms. This proves that an injective mapping is not necessarily surjective. We aren't actually using the hotel's full capacity. To truly solve infinity, we must find a method that leaves no gaps. We need to move beyond prime exponents. Our second attempt uses an algorithmic approach. We designate the current guests as bus 0 to ensure they are integrated into the new numbering sequence from the start. We use a digit interleaving cipher. It takes a passenger's seat and bus coordinates and physically weaves them into a single integer. If we take seat 1, 2, 3, 4 on bus 0, 7, 8, 9, we stack the numbers and alternate their digits. The result is a single zipped room number, 01728394. We can reverse the process just as easily. Extracting the alternating digits makes the original seat and bus numbers reappear. This method fills every room sequentially. Every integer corresponds to a passenger, and every passenger has an integer. But this trick is tied to the rules of our base 10 number system. To find a universal truth, we need a solution based on pure geometry. We can visualize infinity not as a string of digits, but as a structural map. First, we place original guests into rooms that correspond to triangular numbers. This fills rooms 1, 3, 6, and 10, creating a geometric skeleton for our hotel. The infinite buses and seats are then plotted on a two-dimensional grid. Every possible passenger now has a specific coordinate. To assign the remaining rooms, we use Cantor's diagonal pairing function. This method sweeps across the coordinate grid, assigning a unique number to every point in a precise sequence. This geometric path targets the spaces left empty by our triangular numbers. It maps every bus and seat combination to a vacant room without skipping a single integer. By utilizing spatial geometry instead of arithmetic tricks, we create a blueprint that accounts for every dimension of the problem. Watch as the two-dimensional grid of buses and seats begins to fold. It is physically collapsing into a single infinite line. The Cantor formula is designed to map passengers to the exact room numbers left vacant by the triangular sequence. As these two sets of values combine, they fill every consecutive integer from 1 to infinity without exception. This state, where every room is filled and no guest is duplicated, is a perfect bijection. This geometric arrangement ensures that every passenger, no matter how deep their position in the grid, has a predictable, balanced location. Within this structure, the overwhelming scale of the buses and seats is resolved into a single calculable address for every individual. Through this lens, mathematics maps an entire two-dimensional field into a single manageable sequence. Now, try to apply this geometry yourself. If you use the pairing function for bus 2, seat 3, what is their exact room number? calculate the answer and leave it in the comments.